All right, so I did just want to talk a little bit first about brown dwarfs. So to tell you a little bit about myself as a more traditional scientist before we go into this other realm of software development. So I'm an observational astronomer. So here's an artist rendition of brown dwarfs, the types of objects that I study. So they're much smaller than the sun. Let's see, I can start. Ooh, I can even see maybe there. Can you all see my mouse? There it is. And can I see it there? Yes, I can. All right, so the star which we're most familiar with, our nearest, closest star is the sun. The types of objects that I study are about 0.7 times, 70 Jupiter masses is another way of thinking about it. So we're also familiar with Jupiter. The types of objects that I study are about the same size as Jupiter, so they're about the same radius, but they're 70 times the mass of Jupiter, or 0.07 times the mass of the sun. For some of them, the highest mass ones actually fuse hydrogen in their core, so that makes them star-like. That's the characteristic thing of a star, is that it fuses hydrogen, maintains hydrogen burning, stays the same luminosity for billions and billions of years, at least as long as we care about. But brown dwarfs don't sustain hydrogen fusion in their core. And so as a result, they gradually cool with time. And so brown dwarfs are always changing. They're always cooling. What makes them both, really fascinating and really interesting, but also a pain in the ass, is that they're so cool, their atmospheres are so cool that they have condensate clouds in their atmospheres. And so one of the characteristic condensates that they have in their atmosphere, I don't even know if it's a condensate, but whatever, a metal thing, is liquid iron metal. And I once asked a theorist, I was like, what is liquid iron metal? How am I supposed to visualize liquid iron metal? He was like, oh, it's like suspended BBs in the atmospheres. And it's like, all right, I'm trying to understand the physical nature of objects that have suspended BBs in their atmospheres. Like, this is ambitious. And so they have cloud layers and probably a lot of the similar cloud properties that Jupiter has, but at higher masses and hotter temperatures. So clearly I don't study the cartoon versions. I'm a spectroscopist, optical and near-infrared spectroscopist. And so when I say that I study brown dwarfs, these are the wiggly lines that I'm trying to interpret and say I wonder where the iron BB is. The iron BBs, if I get more iron BBs, does this line get deeper? And so you can see how this is the potassium absorption line. And so in this particular object, which has this lovely characterization of VLG versus intermediate G and field G, that the potassium lines have different shapes. And so this is actually the methods that the type of data that I analyze and try to interpret the physical atmospheres, the physical properties of these very low mass objects. What's important to note is that I did not, now I'm going to very gracefully transition to talking about something completely different. I used a computer to make this figure. I didn't use Python. This is an IDL figure. And then I also used probably a combination of PowerPoint or Keynote to add the highlighting, things like that. So even though I've never been trained in computer science, I've never been trained in data visualization either, an everyday part of doing my science involves computer and involves coding and software. And so, we have this picture in our head of someone doing science and examining with our eyes and saying oh, this is this color, or reading off a mass measurement or something like that, and then maybe recording it in a lab notebook with a pencil or a pen. No, you're not supposed to keep your lab notebook in pencil, right? We learned that in school, right? You're not supposed to use your lab notebooks with pencil. It's supposed to be with pen because it's a record and it's supposed to be reproducible, and we're supposed to have a log of everything that you did because that's science. But we don't use pens anymore to do our science. We don't even really use pens to record our measurements. Everything that we do is in front of the computer. We have all of our instruments attached to the computer. The computer's we're using a piece of software to take the measurement. We're using a different piece of software usually to analyze a combination of measurements. And then maybe we're using an even yet different piece of software to visualize the measurements. So science is software. It is deeply embedded in everything that scientists do. This is a picture, I don't actually remember her name, maybe someone else does. This is Hale's wife looking through the Hale 200-inch telescope in Southern California. So when we think of observational astronomers, I go and I use my eyes to look at things. This is not what observational astronomers look like. This is what observational astronomers look like. So this is the control room of the Keck telescope, of Keck 1 or 2. Someone probably can tell which one it is. I can't. And they're not only do they have multiple screens, there's probably also, maybe even 10 different pieces of software that they're using to control the telescope, acquire their observations, and analyze their data in real time. So you can even see they're using a spectrograph. And so here's an output of their spectrum. That's right there. So from the very beginning of the data, at the data collection stage, we're embedding software. So software has made science, I would argue, more efficient, right? So we're using it for a reason. We wouldn't be using it if it didn't make science better. One of the things that's very near and dear to my heart is information sharing. And so one of the reasons why I'm up here giving this talk is because I've realized from a very junior part of my career that information sharing increases productivity. I think this is also generational. It comes from the internet, comes from social media. We have a lot of access to information. And so we don't necessarily have to go to the library to find something out or call someone. We can Google it, or even easier, we can post on social media and someone who we don't even know can answer our question for us. Classically, information sharing has always been a part of academia, has always been a part of science. That's what coursework is. Coursework is information sharing, right? Newton did a bunch of examples, did a bunch of experiments and results and found these great theories. And now in our intro physics classes, we share what Newton figured out. The problem is that these days we're not efficiently sharing all of the things that we have learned about using software and using computers to do our science. It's also, for my generation and younger, information sharing doesn't look like textbooks anymore. It looks like the internet. We share information differently, and we have far more tools to share information in a variety of ways. And so just to give you a little bit more context about where I'm coming from with efficiency, so in 2009, is it 2019 yet? No, so 9 years ago, April 11th, wow, almost, I never celebrated Astrobetter's birthday. Maybe I should. Maybe we should do something April 11th, 2010. Someone record that. Someone record that idea, please. I started a blog specifically to facilitate information sharing for astronomers about using their computers. And so I did say specifically, Macs were not 100% adopted at the time. This was my way of limiting the scope of the blog. I was a Mac user, and so I wanted to limit it just a little bit. But I wanted to give us other astronomers, us scientists, a way to share all the information that we're figuring out about how we used our computers to do our work. I had always envisioned the blog as being a shared effort. So it wasn't ever going to be just me, so I always had it set up as a list of contributors. I have been the most prolific contributor, but you can see guest is the second most, and so lots of people have contributed blog posts. And this remains a project which is near and dear to my heart as a venue in which astronomers can share information. And as far as I know, there are not that many other subdisciplines that have such a consolidated resource. Another thing that we have on there, it's not just the blog, which is kind of like news items. There's also a wiki, which allows people to edit things and add their own wiki pages. And so there's like data reduction guidelines and things that are very specific to astronomers, but not specific to individuals, to groups of astronomers that that don't know each other, right? So they're not co-located. So that was 2009. In 2011, so I didn't use Python. I don't know why I was on this mailing list, is basically my point. So I was on a Python users mailing list. And so this is the origination email, which we've seen. I really wanted to work this into this talk because other people have shown their origination email slide, and I wanted to show mine. And so Marshall Perrin made this excellent point that we have these proliferating astronomy packages to do overlapping functionality. So there was AstroLib, PyAstroLib, AstroPySix, PyAstronomy. A couple of them did wavelength conversions, and a couple of them also did coordinate conversions in precession. I also want to point out that they were almost all on different websites. So one was on python.org, one was on SourceForge. I don't know what track6.assembla is. Right, they're all on hosted on different places. And Marshall made this excellent point, which these days, he prefaced it by being provocative. These days is actually not provocative, which is the whole point of this talk, is that as a community, we are doing something wrong if everyone wants to start their own new module rather than contributing to a common, shared, open source core. And that was provocative. And we're clearly doing something wrong. What do we need to do differently? How can we make it easier to use a shared repository and shared namespace for all of this? So I didn't have questions. I didn't have answers to how to use Python questions, but we want to organize a group of people. I'm in. I have opinions. Let me help. So I responded to this email, which I had actually forgotten about until I started actually doing research for this talk. And so in my nature, so one of the things that I wanted to be a little bit a theme of this talk is that not only do I care about efficiency, I also care about management. So I care about taking care of the community and figuring out what the community needs in order to function. And so that's a role that I play. And apparently it's a role that that I played since 2011, even though I'd forgotten. So I volunteered to say I'm happy to participate in helping form this group as a non-Python programming expert and maybe provide the voice of the users. And so I still strive to provide that voice, even though since I've been involved in the project now for a while, I've learned a lot of Python since then. And one of the things that I did that I took some leadership on so this talk is in honor of the fact that we're having the Python and Astronomy Conference here in this space this week. And so I'm sort of speaking to two audiences. There's an audience that I've been interacting with all week, and then there's the audience who are here just for the lecture. At the Python and Astronomy Conference, I want to say 3 or 4 years ago, we really sat down and established some roles in the AstroPy project. And we got people in charge of things. And I was really proud of that. And we did it for multiple reasons. But I was also very happy to find in this email from 2011 that I had that idea right from the very beginning. I was like, maybe if y'all sit down, I'm not going to go to this meeting. It's in Austin. It's too hot. But if y'all go, this is what you should do. Maybe even assign some tasks, create some leadership roles. And gave some examples. And I'm very proud to say that for the past couple years, we have roles established, people filling them in, and it's a really important part of the sustainability plan for the project. So why? So I'm using AstroPy as an example of the types of large open development code projects that exist. So you saw one reason why we need to do it, right? We need to stop reinventing the wheel. Many people were establishing the same code base, writing the same things. That's inefficient. It's also, the knowledge of the whole, the knowledge of the individuals is not as good as the knowledge of the whole. We can write a better code base if we work together. There are other really important reasons to do it, and important reasons to make the code more visible to the community. And so I thank Danny Ryan for the inspiration for this slide. So this is part of a talk that he gave a couple days ago. So from a paper on solar physics, so the text says, to calculate distances and areas on the solar disk, firstly, helioprojective coordinates are converted to heliographic coordinates. Okay, so they did a coordinate conversion. Fine, they said that they did it using the world coordinate system available in the standard solar data analysis software, without providing any other information about which script or which version of the script or which date of the script. And so Danny points out that there are 3 different ways to do this conversion in the standard solar data analysis software, 3 different ways that give 3 different results. And so you can see that 459.149 is significantly different than 459.07, which is again significantly different than 459.1486. So if we care about reproducibility in science, and we know that software is at the core of doing science, we have to be handling our software. We have to be treating software differently. And so one of the important things about this whole open source software movement is at the core a desire for science to be reproducible. This is one of several XKCD cartoons. And so I don't know that we know this character. Does this character have a name? No. Okay, so the XKCD character pulls a lever, gets struck by lightning. A normal person says, I guess I shouldn't do that. But a scientist says, I wonder if that happens every time. So we want to be able to reproduce experiments and get the same result over and over again in order to understand how nature works. So we want to, and the lowest hanging fruit, right, something which we think is a basic expectation for science, is that if we have the same data and we have the same methods, we would get the same results. But in order to show that science is, so I want to do a little bit of an aside here, because I know we have an interdisciplinary audience. That concept is known in some fields as reproducible, in other fields as replicable. And the nomenclature is extremely confusing. And Lorena Barba wrote an entire paper on the different usages of reproducible and replicable in various literature. So I tend to say reproducible, but it is also known as replicable. There's another concept which could either be reproducible or replicable, which is just different, is using different methods, different data to get the same result, which is also really desirable in science, but not necessarily the topic that we need with respect to open code and open software development. There's also a whole nother topic on this slide, which is open data. And so I'm not going to talk about having access to the data. That's a whole nother thing. What I am going to talk about is having access to the same methods. And so in that example that we saw before from the solar physicist, they described their method, but they didn't provide it to us in a way in which we could consistently reproduce it. And we do not, well, until recently, we don't necessarily have a culture of sharing that level of detail in our papers in order to make our science reproducible. That is rapidly changing, which is what I want to talk about today, and also show you the workflows that we use. Many people will say, oh, all I need to do is make my code open source, and then everything will be okay. Open source is a phrase which maybe some of you have heard before, maybe some of you haven't heard before. I would like there to be an interactive activity at the moment. And I would like you to chat with your neighbor for about a minute and try to talk to each other about what you think open source software means. You have about a minute, go. Let's bring it back in.
You can just throw some code over the wall.
And I'm going to ask if anyone whose thoughts about what they thought open code software changed in the past minute, if they want to share with us what they thought it was before and what they think it is now. Anybody's ideas? Okay, well, Eric? I feel like Eric knows the answer. Eric's a plant. No.
Normally I make. Should I say it? Normally I would make a distinction between just open source and open development, where open source is you can see the source code. But it occurred to me in this discussion just now that there's actually two kinds of open source. There's you can see the code and you can see it and actually do anything with it.
Excellent.
Totally different.
So Eric made a distinction between open source code and open development, which are two different things. Thank you for that. And then there's also two different types of open source, which is one where you can see the code and one where you can use and modify the code, right? So there's some different concepts. Anybody else have some? Abby?
I was just going to say this was a revelation that was independently had by Leah and I during that same minute.
Okay, independent realization. Go ahead.
A good example is LibreOffice, which many of us are familiar with, where there's a worldwide community of developers that can submit improvements or bug fixes to a central committee, and if they get proven, they actually get released into the software.
Excellent. So this was an
So download all of the software and modify it for your own use
right.
on your computer.
So two different things. So the example was LibreOffice, where you can submit changes to LibreOffice, and it goes through a committee, and they review those changes. And you can also download the code, change it, and then distribute it as something different if you want it. So we're touching on lots of topics. So I both loved and hate this Wordle when I found it, because what open source software really, really is as at its base is a license. And I was like, where's the word license in here? Let me fix that for you. So the open source definition is a piece of software whose source code is made available under an open source license. In order for code to be, so we use, a lot of people will just say a code is open as shorthand for its open code software. It's not open unless it has a license. So in an open source license, this is a very rich topic, and I just kind of want to scratch the surface of it. But an open source license grants anyone the rights to inspect, modify, and distribute the code. And so that was the last little thing that we got about the LibreOffice, with some possible caveats. So there are different flavors of open source license. Putting code on my web page makes it open. False. If it doesn't have a license, it's a copyrighted, all rights reserved. If somebody used it, modified it, and distributed it, they could get sued. So code can be visible to you. You could put your code on a web page. You can put your code on GitHub. But if you don't put the license on it, it is not open. Yeah, I like that. That was some aha moments right there. That's awesome. If I make my code open, I must support and maintain it. Good. Also false. This is a common misconception, so that making code opens mean other people can use and modify it even if you abandon it. And so I didn't put this in my intro. It's really relevant, though, so I'm currently on a National Academies panel to develop an open code policy for the Science Mission Directorate of NASA. And many of the white papers which we received said, you can't make me make my code open, because then I'll have to do all this more work to address all the user concerns. And it's like, actually, no. That's not what we mean, right? Putting the license on it lets other people mess with it, even if you go silent, and it empowers other people to use it and distribute it and take advantage of the work that you've done. Anyone can participate in the development of open code. False. There is a difference between open code and open code development and open development. So you can, at home, not on the internet, write your code and then just distribute it with an open code license, but involve no one else in the development. So someone else can then take it and be like, okay, you don't want my help? Fine. I'll just make a different piece of code and call it something different and redistribute it. But a person does not have to include other people in the development unless they want to. And so that was the distinction which Eric made between the difference between open code and open development. And so what I really want to focus on today, so I almost even want to go back. So Marshall, in his email, was very, I think the word is prescient, some fancy word. No, it's not that one, it's Marshall's. It's this one. Dude. So it's a common, shared, open source code, right? So he was very specific, right? He said that the code needed to be open and it needed an open development model. And so those are two different things which are really important to distinguish between. And what has really revolutionized science, in my opinion, is not necessarily just open code, but open development. What has made open development possible is GitHub. And I did a lot of research on this in the past couple days to try to figure this out. And a lot of people were developing code, using version control and putting their code on the internet before GitHub. But GitHub really made it possible for people to discuss, collaborate, and make changes to code in a not unrealistically burdensome way. So it's a repository to store, exchange, trade, talk about code. This is an amazing stat, I thought, that it is the 32nd most popular site in the US. That is astounding to me, that a site where people upload and talk about code and programming it's more popular, more popular than Yelp, Hulu, Walmart, and Wells Fargo. Yeah, anyway. It's a big deal. Yes, okay. So GitHub does some really important things. It gives us version control. So version control isn't new. That's the thing which we need to have software development. We need to be able to roll back things. But it makes code accessible. So projects are discoverable. You can search on various things, and widely accessible. So all you need is the internet to be able to find it. And it's not... it's also all in one centralized location as opposed to distributed, on individual websites or at universities' websites. It's in one place. It's also transparent if you choose to make it so, right? It can be transparent, which is that work in progress is visible. So someone can start you don't just see the final product. You can pay attention you can see code as people make the changes to it. It's collaborative by design. So all of the working as a team and everybody contributing to code and making comments on the code is all built into the system from the very beginning. So it is social media plus programming in a beautiful, beautiful way, which we've taken advantage of. One of the other things which I added, that I've added to this list and I didn't take from this really excellent, so the Octocat That Changed the World is actually a really excellent article that talks about the impact of GitHub. I learn a lot by looking at people's code on GitHub. And so it's a really great educational tool. So all of the above things, that is accessible, transparent, and collaborative. Not only can I look at the code, I can also see what really experienced programmers think about the code and say suggested to someone else that they should use this method instead of that method. Now I know that that method exists, and you can see all the explanation. So it makes learning how to code much more accessible as well. So I want to, because GitHub is the thing which has really made open development possible, I want to spend a little bit of time talking about the GitHub development workflow. And so here's a beautiful infographic, which I'm going to try to go one bit at a time. So we can imagine that there is a team of people who I think in this case are wearing the shirts in the infographic, are the like the origination team. So they create the project, and then there are some users who use them. And so in this particular case, this user says, hey, wouldn't it be great if the code did this in addition to the stuff it already does? And so this is posted as an issue to GitHub on the internet. The team discusses it with the user. There's some changes made to the code. Notice here that the user doesn't need to be involved in every conversation. So here's a conversation between two team members who may be the most proficient with the code. And then so every time there's a circle, the code is changing. So there's a change in the code when there's a little node in the graph. So this is a branch of the code. So they decided to take it off into some other working environment, not where everybody sees it. And then it's merged. So we've gone from a user suggesting an issue to being involved in the discussion of the implementation to that feature now being available for everybody else who uses the code. Another possibility, another thing which happens a lot, which is that there's a whole nother team. There's a whole nother independent team that says, hey, this code is really close to what we want to do, but it needs some major changes in order for it to work for us. So they just take the whole thing, they make some changes, usually some pretty significant changes, and then they issue what's called a pull request. So then they're telling the original team that says, hey, we made some really big changes. You might find them useful as well. But now you have the option to include them in the original code base or not. And so now the team discusses, they maybe make some changes, and we're like, oh, we weren't sure that that's what we were thinking. Okay, let's compromise, let's have this conversation. And then they come to a mutual consensus, and then those changes are then merged back into the main branch. Every once in a while, the team decides that we're actually gonna, call a release and do a major thing, and so that's usually just among the primary team members. And then when a new release is made, the user has a great sense of satisfaction because they contributed to a big change. The other team is like, this is awesome because now we can use this, and now they have twice as many people working on a code which benefits everyone. And so all of this happens on the internet. On GitHub is where all this conversation happens. It is you can even see by the complicated nature of the graphic, it's not the most user-friendly workflow to get into, but once you get the swing of it, it is extremely powerful and is really driving the software development that's happening in so many areas of science right now. Anybody have any questions about GitHub? This is my last slide on GitHub.
Command line, or you use the click?
So the question was, do you use command line or do you click? You can use the command line to push your code and to perform what's called the commit messages, so just to describe the changes that you've made to the code. All the discussion with other people happens on the GitHub website in a GUI. Does that answer your question? Yes. Other questions about GitHub? Okay. So the other thing which has been made, which has really changing the nature of scientific computing, is the rise of Python. And so for me, I just trusted other people. Like, people told me, like, okay, you should use Python. And I was like, okay, I trust you. Like, I didn't need to make a decision. Again, I did some research to figure out why it is that Python became the choice. So Python plays very well with other codes. So it works very well with C++, among other things. It's powerful. It has a large ecosystem of third-party modules. It's also super easy to learn, which that was attractive to me. So that it was very easy to learn, so it's a low barrier to entry, which isn't necessarily the same for codes like C++. Python also is developed in the open. So Python has a whole ethos that encourages open source development and community development and coming to consensus. And so it's a community-driven development model, which I think agrees very well with the scientists who are trying to get things to be more in the open in the same desire to get things to be more reproducible. One of the most compelling things I think for astronomers was that Python is zero cost. So the coding language before Python we were using was called IDL, which doesn't matter what it was called, it's expensive. And so not everybody could use it, which is a huge problem. I don't know what's happening. Oh, thank you, Fitbit. I've had 30 active minutes. Yay. So Python is zero cost. It's free. That's not just great, like, yay, I don't have to charge my grant as much. But in terms of getting more and more people involved, so in low-income countries or from even low-income universities and high schools and colleges, anybody can download Python and then run the scripts that scientists are writing. So Python I'm being very careful not to use the word free, because free means something different, which I didn't want to get into. Python is zero cost, which is also very compelling. Python has been widely adopted outside of science as well. So one of the other great things about Python is that it's an extremely transferable skill, which is another topic which we talk about when we talk about science education, is that we really want our students to be able to have, our undergraduates and our graduate students to have options when they graduate. And so having students learn Python means that they can move into a wide range of technical careers. And so this is the number of pull requests, so the number of sort of major code contributions, that's the number, the x-axis, on GitHub in 2017. And so in 2016, Python was actually number 3 behind Java. And so in 2017, Python overtook Java for the number 2 slot. And I consulted with Adrian, and he tells me that JavaScript, Java, Ruby, and PHP are all web development, mostly. And so Python is really the one in there that can be used for scientific computing. So it's very, very popular, not just with scientists. One of the other reasons that scientists are converging on Python, so this is all of the other packages which you can use with Python that gives it so much functionality. So Python is at the nexus, at the hub. So there's also NumPy, which I want to talk about a little bit. NumPy, I just say it does math. I don't even think that's right. I think it basically enables you to manipulate arrays, but it's a very basic functionality you would expect for the programming language. I assumed that NumPy was just built into Python. It's one of those things that you always use in every piece of code. NumPy isn't built into Python. It's a completely independent package and actually not that much different than AstroPy. And so independently written by academics that were like, hey, we really need this thing. Let's work on it together. So, but this is fundamentals of scientific computing. There's also Matplotlib and Bokeh, which are used for visualizations. Pandas is used for manipulating big arrays of data, tabular data. Pandas is used extensively, not just in academic science, but in industrial data science. So, Google and Facebook use pandas to analyze all of their data and to figure out what ads to serve you. SciPy and scikit-learn, or this one, provide a lot of statistical tools and analysis tools. I don't know exactly what SymPy does, but so here we are. We made it to this graphic. So AstroPy and SunPy, which has lots of representation in the room, are also, so it's a domain-specific things that make Python really powerful for astronomers. So yeah, scientists are converging on Python. We're using it to develop, and we're also using it to do our science because so many other scientists have developed these extremely powerful packages. So this is now a Stack Overflow plot to show you how, so among the general community, how much the scientific packages are being used. So this is the growth. So this is traffic to questions about selected Python packages. And so the blue one here is Django, which is web development, right? Pandas has now overtaken Django, which is used pretty exclusively for data science. And then there's NumPy and Matplotlib and Flask, which is also for web development. So the scientific Python packages are getting lots of use inside academia and inside science and outside of science. So if it's on Stack Overflow, it's lots of people. But the point is that scientists are converging on Python, and I modified this XKCD slide, but just to let you know, like, it's not just me that thinks that. Like, if they make a cartoon about it, then it must be true. And so you see someone who's flying, and he's like, "How are you flying?" He's like, "It's Python. How did you do that?" "I just typed import anti-gravity." That's it. And then, there's some other things, but he's pretty sure it's the Python. And so that can often be, sometimes I ask questions, someone like, "Oh, how do I do this?" And there's like, "Import this." And it's like, oh, okay. It's a very readable language and a very intuitive language compared to other things. So that's the good news, right? So we have GitHub, which has changed the world. We have Python, which has even changed our world more because we have these packages which not only astronomers use, but the data scientists use, which means the biologists can use it, the economists use it. Lots of people are using Python, and that's great because we have the collaborative code environment, so lots of people are making a common code base super awesome. There's a problem, though. So some of this most vital code is maintained by a very small number of people in kind of precarious job situations. And so a lot of these packages were originally developed and maintained by graduate students or postdocs or research staff, essentially in their free time. And so NumPy has 6 current maintainers. It's great, though. So some of these numbers are impressive, which is the number of contributors, right? So that they're, in these 600 to 700 contributors is really great. The number of maintainers is a problem. And so it's also a problem because so many things are now dependent on these code bases. We have a vulnerability in our scientific infrastructure which doesn't have a clear solution. So this grassroots thing has been awesome, but now we have this new problem, a new problem to solve, which is how can we, I don't necessarily want to say formalize, but provide stable infrastructure to these code bases which are openly developed while maintaining their still awesome community and being developed in the open characteristics. And so there is a nonprofit organization specifically dedicated to this purpose, and that organization is NUMFOCUS. NUMFOCUS does not have nearly as much name recognition as it should have in the scientific or the open coding community. So NUMFOCUS is stepping up, is developed was established to provide the, let's see, I can probably just go to the next slide. The critical needs of open source projects, specifically with scientific computing. So they want to be able to house funding, they want to provide stability, they want to help us maintain independence, and they also want to provide logistical support. So remember, the almost all of these projects are not centrally located at a particular institute or in a particular research group. Everybody just met on the internet and was like, hey, let's make a thing together, and they did. And so and most people have been doing it in their free time. And so it's not clear who should pay for it. Who should be paying the people to contribute to solving the issues or collaborating with the other teams to implement new things. So one of the things which NUMFOCUS is really helping us with, it's also one of the challenges is that it's a lot of active scientists who don't necessarily think a lot about the fiscal problems or maybe legal implications of things. And so NUMFOCUS also helps provide us with some of that because the developers really just want to be like, no, I just want to implement this new thing. I don't want to think about how I need to pay someone next week. And so it's giving us some of that management encouragement as well. So it's also giving us some of the fiscal legal services to help really forcing us, I hope, to figure out our sustainability model and giving us infrastructure to help grow our various communities and a community with each other. So NUMFOCUS is it's called the fiscal sponsor. So the fiscal sponsorship means that if any one of these organizations gets money, then NUMFOCUS will hold the money for them. I think that's a good way of thinking about it, for an impressive number of open source projects. One project which I haven't mentioned, which is the Jupyter Notebooks. So many people use Jupyter Notebooks. We use Jupyter Notebooks a lot when we start to code. And so that's a NUMFOCUS project. NumPy, Matplotlib, Pandas is a NUMFOCUS project. And so for me, as part of the AstroPy project, 2-3 years ago, I was thinking, how can we get money? How can we figure out our community problems? How can AstroPy figure out our code of conduct? I don't think that way anymore. Now I think about how can AstroPy, as part of NUMFOCUS, figure out a community model which works for lots of open source projects? Or how can we get funding which supports all these open source projects, which are interdependent upon each other and all awesome because the other one exists? So if I look into my crystal ball, right, so I look back on the past 9 years and I look forward, given our infrastructure, I think in the future of academic science, software development skills will be considered fundamental and essential. Right now, they're a little optional. It's like we still kind of pick them up as we go along. I don't think that's going to last very much longer. I think it's going to be a basic expectation. And what I mean by software development skills is not just the ability to use GitHub or the knowledge of these packages. It's also making sure that the packages are reproducible and verifiable. So there are other things which I didn't talk about too much, which involves implementing testing infrastructure into your code. And so there are industry software development best practices which scientists are going to need to start learning and implementing how to do. Software will be considered a research product similar to a journal article. So I think so there's a Journal of Open Source Software, which I don't have time to talk about too much right now, but that's really helping move us towards the direction of having software treated in the same currency as a journal article. Code review, I think, very shortly is going to be part of the peer review process, and that's going to be painful for some people. It's going to be a forced eye-opening. The junior folks who are at this conference are going to start peer reviewing papers and being like, "Where's your code? Where's your tests?" And authors are going to be like, "Who do you think you are asking me to do this stuff?" And they're going to be like, "I'm the referee. Where are your tests?" And so I'm hoping that peer pressure will force changes soon. Especially because I'm on this, committee to develop an open code policy for NASA. I think it will be very shortly that all code will be expected to be open and accessible, especially federally funded research, code from federally funded research projects. So that doesn't need to be open developed. That doesn't mean it needs to be maintained and supported, but that the code that you use to come up with your result will need to be open so that someone else can at least see it and modify it if they want to. I also think that contributing to open collaborative projects will be the norm. I don't know that I have a good analogy for that right now, but I think that all these projects have really demonstrated that it's in science best interests for us to be working on common, if we have a common infrastructure, that we can all benefit from that, rather than people reinventing their own scripts to do their own things. No one teaches us how to do any of these things, though. Where are we going to learn? How are we going to learn that? And I don't have good answers for that. This is the last XKCD comic. But our education must change. And I've been a professor now for 7 years, and changing the formal curriculum is very, very challenging. The only hope that I have, and it's combined with a lot of the efforts that I do at the AstroPi project, is that we basically need to infiltrate the formal curriculum with software development. So we can take an introductory physics class or an introductory chemistry class and add coding assignments which cover those same materials into it. And that's going to take creativity, and it is going to take some things may not get covered as much. But I think that that's the way forward, is to integrate software development and coding practices into the existing curriculum. And so the slide is the 11th grade activities, usefulness to career success. So one of the low bars is 900 hours of classes. There's another low bar, 400 hours of homework. But then the thing that was the most useful to the career success is 1 weekend messing with Perl, which is a software programming language, which at least for me has been extremely true, that a little bit of time learning how to code has paid off really substantially. Learning to code on my own has paid off really substantially in terms of career success. So conclusions, science is software. I didn't spend too much time trying to convince you of that. I think it's pretty evident. GitHub has facilitated open development, right? Not necessarily the open code, but the open development has been the key, and GitHub has helped us with that. And it's really changed the way we interact with software, and is going to really change our expectations as scientists when it comes to sharing and what software looks like. Python is rapidly becoming the common language of science, which I think is a really great thing. I think that's going to help with interdisciplinary research and cross-collaboration, cross-pollination of ideas. NUMFOCUS, so James is also here, he's the vice president of NUMFOCUS. I invited him. I didn't give NUMFOCUS all the cred because I knew he was going to be here. I wanted to really highlight NUMFOCUS, and I was like, oh, you should really come to my talk. So James is here. Really needs more name recognition as a vital part of the infrastructure of science. And software development needs to be taught and integrated into the formal STEM curriculum. This is the hardest thing. The last thing is I think the hardest thing, because we need to convince a lot of professors to learn new tricks, and that's hard. Thank you for your attention.